So let's look at a volume problem here. We have a balloon that's being inflated with gas, and we know that it's growing at a rate of 800 cubic centimeters per minute. So that is the change in the volume. Cubic centimeters is the volume. So it's good to write that down. Cubic centimeters per minute. And we want to find out how fast the radius is growing. All right, so how fast is the radius increasing in size? So we're going to have two parts here for that at the end. So we need to connect these two variables. We need to start with an equation that connects the radius and the volume. All right, so cubic centimeters is a volume. All right, so what is that volume formula for a sphere? Well, the volume is 4/3 pi r cubed. That's not necessarily one that you'll have to have memorized. It's a good idea, but that'll be given to you on a test, most likely. So if we have, there's our volume. Now we need to find the change, the derivative, the rate of change, that is, with respect to t. We're going to find the derivative of both sides. So we're doing this implicitly. Volume is changing in time, so the derivative of volume is just dv dt. Here we have a function of r. So to find that derivative, we need to do the chain rule. So we take the derivative of the outside. In other words, kind of just take the derivative with respect to r. So we take the derivative of this with respect to r. We drop that 3 down. 3 times 4/3 is 4 pi r squared. Now we need to take the derivative of the inside using the chain rule, and that is dr dt. Okay. So great. Now we have r, dr dt, and dv dt. So 3 variables. This whole thing here is one unknown. So now we can go to these two parts. We have, we want to know what's the instant, the rate of change of the radius. We want to know how fast the radius is changing, dr dt, when we know that the radius is 30 centimeters. So if we got the radius is 30 centimeters, and we also know that dv dt is 800. So we've got 800 equals 4 pi times 30 squared times dr dt. And we want to solve for dr dt. So basically we need to multiply this. That's 900 times 4. 900 times 4 is 3600. Divide both sides by 3600 pi, and we end up with 800 divided by 3600 pi. Okay, and that will be dr dt. Flip it around here. That simplifies to 2 over 9 pi, which is approximately 0.071, and this would be centimeters per minute. Okay, now we're going to do the same thing, but what happens when the radius is 60? It's changing at a different rate. So let's check out when A is, or let's part B, when the radius is 60. Well, we have 800 equals 4 pi times 60 squared dr dt. 60 squared is 3600 times 36 times 4 gives us 14,400 pi. So let's just go ahead and divide that over. How about that? Why not? So we divide both sides by 14,400 pi, and that's dr dt. And that simplifies to 1 over 18 pi, or approximately 0.018. and that would be centimeters per minute. Okay. All right, so that's the idea. Once again, big idea. We will we want to get an equation, this red one up here, that connects the variables. Then we take the derivative with respect to t to get our rates. Okay. All right. Let's look at a cube here. We got a cube, and we see that the volume is changing. Well, it's expanding. All the edges are expanding at a rate of 6 centimeters per second. So we have these edges here. All right. So we can call these, maybe they're all the same. You can call them S, or use a different variable if you'd like. Okay. S gets a little confusing. How about we'll call them X? They're all the same. It's a cube. That's important. So volume is length times width times height, or x to the third power, x times x times x. So we need to, there's our equation, connects volume and connects the edges. The volume's changing and the edges are changing. Okay, we're looking for how fast the volume is changing. So let's go ahead and find the derivative with respect to t here. So we have dv dt. And implicitly, take the derivative here, drop the 3 down, x squared times the derivative of the inside, dx dt. All right. Now, let's go ahead and plug in what we know. We know that the edges are changing at a rate of 6 centimeters per second. So dx dt equals 6 centimeters per second. So dv dt is equal to, now we've got two parts again, so we're going to find this when x equals 2. So 3 times 2 squared times 6. Well, that's 3 times 4, which is 12, times 6, which is 72. And that would be cubic centimeters per second. And when x is 10, we have dv dt. And that's going to be 3 times 10 squared times 6. And that would be 10 squared is 100 times 3 times 8. That would be 1800. 3 times 6, that is, I think I said. Cubic centimeters per second. Okay. All right. So when the volume, when the radius is larger, a lot larger, 5 times larger, that volume is a lot larger there, all right? So, in fact, should be 5 cubed times bigger. All right, that change there. Actually, no, since we're talking about the change, it's 5 squared, 25 times larger. All right, surface area here. So we have the conditions are the same as exercise 18. So we're talking about the cube. Okay, we still have the cube. We still know the dx dt is 6 centimeters per second still. All right, but now we're talking surface area. So if we take the same cube, we want to find the surface area. Well, what's the area of one square? It's x squared. And one face, that is. And there's 6 faces, so it's 6 times x squared. So the surface area is going to be 6 times x squared. So there's our formula for the surface area. So how is the surface area changing? Well, let's find the derivative with respect to time. So that's dA dt equals, now do this implicit here, okay? So drop the 2 times 6 is 12, x to the first times dx dt. Okay? And now plug in what we know. Well, we got our 2 parts first of all. So when the edge x is 2, then we have the dA dt is 12 times 2 times dx dt is 6. That's 12 times 12, or 144. Okay, and this is a change in the area, so this would be square centimeters per second. All right, what about B? We have when x is 10, the change in the area should be 12. Using our formula here, dA dt, 12 times x, which is 10, times 6. So that's 120, well, let's see, whatever, 6 times 12 is 72, times 10 is 720. And so that is, again, square centimeters per second. Okay? All right. So once again, big ideas. We find an equation that connects the two variables, in this case area and the edge, the two things that are changing. Take the derivative with respect to time, plug in what you know, and solve for what you don't. Okay? All right, here we got a situation. We got a baseball diamond. Baseball diamond is a square. I know we call it a diamond, but it's a square. Okay, so those bases are in a square. And we got a situation here, so drawing will help. We got a player running from second base to third base. So here's our player running. My little stick figure. I don't know if he's running or falling down or dancing. I don't know. Okay. All right. So he's running this way. And we know it's 90 feet between the two bases. So let's look at the rest of the problem here. So we got a 90 feet between two bases. The player is running from second to third. And we know his speed is 25 feet per second. And he is 20 feet from third base. And what is the rate that the player's distance S from home plate is changing? So we have a distance from the player, wherever he's at, to home plate. Maybe this is dodgeball. We want to throw the ball and hit the runner. Well, we know, so we call this S, as the problem says. And we got to think, what else is changing? Well, what's changing here is this distance. Call it whatever variable you want. Call it X. So the distance from between third base and the runner is changing, and the distance between home plate and the runner is changing. Since this is a square, we have a right triangle. And we know that this distance from third to home plate is 90 feet. All right, so we need to get an equation to relate these variables. Since it makes a right triangle, we got the Pythagorean theorem. Pythagorean theorem says a squared plus b squared equals c squared. Make sure the hypotenuse is in your c spot. So x squared plus 90 squared equals s squared. So there's our equation that relates all the variables. We don't need to solve for anything because we can take our derivative implicitly. So let's take the derivative of both sides implicitly with respect to t. So d dt of this, take the derivative of the outside, that's 2x, times the derivative of the inside, dx dt. And 90 squared gives us 81. Whoops, that should not be equal, should be plus. 8100, 8,100. Take the derivative of s squared with respect to t. That's going to be 2s on the outside times ds dt. Great. Now let's go ahead and let's see. Let's look at what we're looking for here. We know that he's running at a speed of 25 feet per second. So which one's that? That's going to be dx dt is 25 feet per second. We also know that he's 20 feet from third base at the moment that this is happening, 20 feet. So we want to find out when x is 20 and dx dt is this. We want to find out what ds dt is. Now, we also know one thing. So at the moment that we are concerned with, x is 20, we need to find s. So when x is 20, well, we know that 20 squared plus 90 squared equals s squared. And so we get 400, 8100. And so this is going to be 8500, and we'll square root both sides. We get the square root of 8500. Okay? And that is not a rational number, so we'll just leave it as a square root of 8500 for now. That's fine. So, and that is S. So we got everything we need here. We've got these and this one. So let's plug it in. So we have 2 times 20 times dx dt, 25, plus 8100 equals 2 times the square root of 8500 times ds dt. And if we take this side divided by this side, we get a final answer of ds dt is approximately 49.352. And this would be feet per second. Don't forget units. Okay? All right, that's the idea. Again, find an equation that connects the variables, take the derivative, plug in what you know. The picture is real helpful here, too. All right, so we got one more situation. We have a man 6 feet tall, and he's walking away from a lamppost at 5 feet per second, away from a light that is 15 feet above the ground. And that's shown in the figure here. So we want to know what at the moment that he's 10 feet from the base, what is the rate that the tip of the shadow is moving. So how quickly is the shadow moving? And then the question is what is the rate that the length of his shadow is changing? So we have a couple things that are changing here, right? As he walks away, his distance is changing here. Maybe we'll call that x. And the distance that his shadow, so this point right here, is also changing. Okay? So we want to find out how this is, what's going on here. All right, so let's call that y there. All right. So for part A here, we have these two situations here. Now what's going on is we've got a triangle down here, and we've got this big triangle. What do you notice about these two triangles? Well, they got the little triangle, the big triangle. They are similar triangles. So we know they have to be proportional. If you want to think of it, they're in the same slope. All right. Now, you know what? Let's change this. I'm going to, well, no, that's fine. If that's x and that's y, then what is this distance right here? Well, this is the distance y minus x. Okay? So let's make a proportion. Think of the slope here. We've got rise over run, so we know 15 over the whole run here. That's y. So 15 over y is equal to the rise over the run, 6 over y minus x. Now you could set this up different ways. Proportions can be, you could do 15 over 6 equals, so that's big over small equals big y over small. That's fine. But you need to make a correct proportion, and then we can solve this proportion by cross multiplying. So cross multiply here, we have 6 times y equals 15 times y minus x. And if we clean this up a little bit, 15y minus 15x. And if we add 15x over, subtract 6y, we end up with 15x equals 9y. All right. So we could mess with it more, but let's just leave it like that for the moment. And let's go ahead and take the derivative with respect to t. So x and y are both changing. So we take the derivative of the outside, that's 15 times dx dt equals 9 times dy dt. Now, which one of these do we know? We know that dx dt is 5 feet per second. Tells us that up in the problem. So we can say, all right, so this is 15 times 5 equals 9 dy dt. So the tip of that shadow, if we solve this here, dy dt, 15 times 5 is 75 ninths. Simplify that up, that's 25 thirds feet per second. Okay? Well, part B has a little difference here. Okay, the slight difference is this. Well, how quickly is just this line changing here? All right, so you can do this a couple ways. Maybe let's try this. Let's call that S. All right, so what is that length S? How quickly is that length S changing? You see the difference there? Okay, and let's see if it comes out to be different. It should. So if we say y minus x is S, that's what we're looking for. Okay, just to keep things simple. So let's put S in here. So we have 6y equals 15s. And if we take our derivative like we already did, we have 6 dy dt and 15 ds dt. And that tells us that 6 times 25 thirds equals 15 ds dt. And this comes out to be a little canceling, that's 50. So 50 equals 15 ds dt. And so ds dt is 50 fifteenths, or 10 divided by 5 on top, divided by 5 on bottom, 10 thirds feet per second. Okay? So the tip of the shadow is growing or moving faster. So this whole distance is growing faster than just this little shadow is growing. All right? So that's the idea there, all right? So again, big idea is we need to take our situation. We need to make an equation. First, define the changing variables. Define them in this case like x and y. Those are things that are changing. And then write an equation. Then simplify it if you can. Then take the derivative of that equation with respect to t. Plug in what you know. Solve for what you don't. Okay? So make an equation. Take the derivative implicitly. Plug in what you know and solve for what you don't. All right. Hope that helps. It just takes a little bit of practice. You'll see different situations relate to others. So with practice, you'll recognize these different situations and you'll know right where to start.